Hey everyone, this note is on graphs of exponential functions, and the directions say to complete a table of values for each function using your exponent laws and evaluate with fractions, so no decimals will be allowed here. So let's go ahead and take a look at our first example. So f of x equals 5 to the power of x. So I want to make a table of values for this right here, and in order to be able to do that, I think it'll make the most sense for me to go from like -3 all the way to +3. So right here, remember the x is our input, the y is our output. So like right here, this -3 is going to go in for x here. So how do I do that? I'm going to do f of -3, and I'll get 5 to the power of -3, which is 1 over 5 to the power of 3, which gives us 1 over 125, because 5 to the power of 3 is 125. Okay, so now let's do f of -2. So that would be 5 to the power of -2, which is 1 over 5 squared, which is 1 over 25. So this right here would be 1 over 25. What I'd like you to do next is to pause this video and complete the rest of this chart all the way up to an input of 3, and then come back and compare and make sure that you get the same answers as me. Okay, so these are the answers that you should have gotten. 1/5, 1, this one be careful of because some people will say 0 here, 5, 25, and 125. Okay, so let's go ahead and graph this out. So for starters, we need to label our axes. So this is our x-axis, this is our y-axis. Going by ones on the x-axis seems to make the most sense. However, going by ones on the y-axis does not make sense. I think what would make sense is to maybe go by 5s. So this first block right here would be 5. This would be 10, 15, 20, 25, 30, 35, 40, 45, 50. I know we're not going to show the 125, but that's okay. So if you take a look at this right here, -3 will be at 1/125th. So that number right here is like super close to 0. Like it's pretty much 0, right? So right here, because this number right here is super close to 0, I'm just going to draw it really, really close to 0. 1 over 125 is also super close to 0, but a little bit higher. 1/5 is also close to 0, but a little bit higher than that. 0 will be at 1. 1 will be at 5. Notice how there's really not much movement right now. And then 2 would be at 25, which is right here. And then 3 would be at 125, which is like all the way up here. And that's the power of exponential growth. Like every time you're multiplying by 5, the number's getting larger and larger and larger. And if I go backwards, I'm dividing by 5, which means that my number's getting smaller and smaller and smaller. Notice how my number will never go below 0, because no matter how large my exponent, no matter how negative my exponent is here, or no matter how far to the left I go, it's just going to be a number that gets closer and closer to 0. So this right here is f of x equals 5 to the power of x. Let's try g of x now. Okay, so for g of x, I'm going to create a chart just like I did for f of x, and I'm also going to go from -3 all the way to +3. And to figure this out right here, for example, if I want to do like g of -3 right here, this is going to be 1 over 5 to the power of -3. But because the exponent is negative, that means that I have to do the reciprocal. So I get 5 to the power of 3, which is 125. So this right here would be 125. If I wanted to do g of -2, then I would do 1 over 5 to the power of -2, which again, flip that base, I get 5 to the power of +2, which gives me 25. Just like we did before, pause, continue the rest of this chart, and then come back and see how you did. And And as always, if you have any questions, make sure you write them on the side of your paper, okay? And let me know in class. All right, so let's get ready to graph out our values now that we've checked to make sure that these are the correct y values. So you should have gotten 5, 1, 1/5, 1 over 25, and 1 over 125. I'm going to label my axes x and y. I'm going to go by ones on my x-axis. And I'm going to label my y-axis the exact same way, because if you notice, we've got a lot of the same kinds of values here. When x was -3, y was 125. So this time this is like way up high up here, but this time it's on the left side of the y-axis. When x was -2, y was 25. When x was -1, y was 5. When x is 0, y is 1. And then our numbers are getting gradually smaller and smaller and smaller, but never touching 0. So let's connect these values here. And we'll call this g of x, and g of x is 1 over 5, all to the power of x. Okay, so the next thing I want to do is take a look at like our first differences here. So if you look right here from 1 over 125 to 1 over 25, to figure this out here, I would subtract these values, right? So to find this first difference right here would be 1 over 25 minus 1 over 125. Get a common denominator, do all that good workout. I'm not going to spend the time on that right now in this video, but if you do that subtraction, you would end up getting 4 over 125. And then here, to get this first difference right here, remember our first differences is just like how much it's increasing by or decreasing by. So from 1 over 125 to 1 over 25, this went up by 4 over 25. Well, to figure out how much this went up by, I have to subtract my values. So 1 over 5 minus 1 over 25. We're going to get our common denominator. And when you get your common denominator, this goes up by 4 over 25. And then 1/5 to 1, this went up by 4/5. This went up by 4. This went up by 21 and, 20. And then this one right here went up by 100. So if you notice, there's no rhyme or reason to the first differences. These are not going up by the same amount every single time. Let's look at the other example here for g of x. So g of x, this is actually going down by 100, down by 20, down by 4, down by 4/5, down by 4 25ths, and then down by 4 over 125. So if you see here, like again, there's like really no rhyme or reason here, right? And then if you remember when you did quadratics, we did second differences. So how much is this changing by here? So 4 over 25 minus 4 over 125, you get your common denominator. You get 16 over 125. Here you get your common denominator, you get 16 over 25. Here this is 16 over 5. Here this is 16. And then this right here is going up by 80. Again, there's no rhyme or reason for these first differences or these second differences. Why is that? Because this is not linear and this is not quadratic. Exponential functions have their own way of seeing what's happening here. And instead, we're not going up or down by a constant difference. We're going up or down by a constant factor. I'm multiplying by 5 every single time. And that should make sense to you because that's what an exponential expression is. You just repeated multiplication, right? Here, instead of multiplying by 5 every single time, I'm dividing by 5. Or we could say that we're multiplying by 1/5. It's getting 5 times smaller, so we're multiplying by 1/5. Okay, great. So because this one is getting 5 times smaller, this one is called exponential decay. Because it is decaying, it's getting smaller. And then this one, because you're multiplying, it's getting 5 times larger every single time. This one is called exponential growth. Okay, cool. So now let's just fill in this information here. So y equals 5 to the power of x looks like this. y equals 1 over 5 to the power of x looks like this. So, but what's the domain for each one of these? What kinds of inputs can we put in here? Well, we can really have any kind of exponent that we want. It doesn't really matter. So x is an element of all the real numbers, regardless of what our base is. However, our range is going to be a little bit different. So if you take a look at this right here, our range, if you look, anything can work as long as it's above the x-axis. So this means that we can never touch the number 0 or go below 0. And that should make sense to you, because what exponent can I put on 5 that's going to give me a negative number, or that's going to give me 0? It's not possible. So here our range is going to be y is an element of the reals such that y is greater than 0. And regardless of whether it's exponential growth or exponential decay, that's always going to be the case. Now, because this will never cross the x-axis right here, what does that tell us? We have no x-intercept. Either way, okay? Now for the y-intercept here, we can see that the y-intercept always happens when x equals 0, right? And when x equals 0, the y-intercept here is 1. So our y-intercept here is 0, 1. And the same thing is true over here. When x is 0, the y value is also 1. And that should make sense to you, because any input that I put in here, if I have an exponent of 0, I should always get 1. Now, the equation of the asymptote. So if you look right here, we have an asymptote here. My graph is trying really hard to touch that x-axis, but it just can't. So that means that we have a horizontal asymptote. And the equation of it is y equals 0. And that's true regardless of whether we have exponential growth or exponential decay. So here we also have a horizontal asymptote for y equals 1/5 to the power of x, and it's going to be y equals 0. All right, and then the last thing says, what do you know about finite differences of exponential functions? They're not constant. What do we have instead? We have a common ratio. Which is the base. So I just want to write one last thing right here, that we have y equals b to the power of x, where b is your base. This will be growth if b is greater than 1, and it will be decay if b is between 0 and 1, okay? Again, it's growth when it's greater than 1, because you're multiplying by a larger, because every time you multiply by a number bigger than 1, the values get larger. Anytime you multiply by a number between 0 and 1, the values get smaller, so that would be decay. And that's it for this video. Let me know if you have any questions. Otherwise, I will see you in class.